Chapter 1, Section 1.1, Real Numbers. As you can see, the set of real numbers consists of natural numbers, which are our positive integers, our whole numbers, which we can also refer to as our non-negative integers, our set of integers, which include negative, 0, and the positives, and our rational numbers. Two key words to help you remember the definition for rational. Rational number is a number that either repeats or it terminates. And so I've given you an example of a terminating decimal, and I've given you an example of a repeating decimal. The set of irrational numbers, and again, two key words to help you remember the definition of irrational: infinite and non-repeating. The two most common examples of irrational numbers are pi, which we definitely know is infinite and non-repeating, and any square root of any non-perfect number is an irrational number. We also have the set of real numbers as defined of consisting of all rational and irrational numbers. And complex numbers we aren't really going to talk about for a couple of weeks, but I wanted to introduce the definition. A complex number is a number that has a real part and an imaginary part. And we will get into imaginary numbers here very soon, which will help with the definition of a complex number. So to help keep all of the number systems in an organized manner, I went ahead and set up the tree diagram. We have the set of complex numbers, which again consists of a real part and an imaginary part. We have then the set of real numbers, which we will use every day in math. Those are the numbers that we use every day in the real world. And we've broken that down into our set of rational numbers, which, if you remember from the definition, consists of repeating or terminating. And over here we have irrational numbers. These are those ugly looking decimals. They are infinite and non-repeating, such as pi, or again the square root of any non-perfect number. And from our set of rational numbers we have the set of integers, which remember can be negative, positive, and include 0. And then we have broken off into that the negative, the positive, and including 0. Some properties that we have talked about in algebra for many, many years. I know you've heard of these properties before. We start off with the commutative property, and basically all of these properties hold true for both addition and multiplication. And when I think of the commutative property, I think of one word, I think of order, because really all that's changing from the left side to the right side is the order in which we are adding or multiplying those two numbers. The associative property, I think of the word grouping when I think of associative. So you can see from the left side to the right side, the only thing that has changed is the grouping. The additive identity just means anytime I add 0 to anything, I get that anything back. So 0 is the identity element for addition. And the additive inverse is just basically adding opposites. So what happens anytime I add two numbers that are opposites? I'll always get a sum of 0. So good properties to jot down in your notes. A couple more. We have the multiplicative identity, which means anytime I multiply anything by 1, I get that anything back. So the multiplicative identity is 1. The multiplicative inverse, I also think of reciprocal. So anytime I multiply two numbers that are reciprocals of each other, I'll always get a product of 1. And we're all very familiar with the distributive property. Anytime we multiply anything outside times that quantity inside, we need to distribute with each of those terms. Getting into some notation for reciprocals, anytime you see something to the -1, it really just means a to the -1 is the same as 1 over a to the +1, and this is going to lead us into negative exponents. So again, 2 to the negative 1 is the same as 1 over 2 to the positive 1. When I take a quantity to a negative exponent, so 3/4 to the negative 1, that's the same as 1 over 3/4 to the positive 1, which is the same as 4/3. Remember, anytime we divide fractions, we end up multiplying by the reciprocal. So over here we have a times a to the negative 1. So a number times its inverse, or a number times its reciprocal, always yields a product of 1. The property of quotients, I just put this in as just a quick reminder for us. We know that when we add two fractions together, we have to have a common denominator in order to add those fractions. And if we don't have a common denominator, we have to find a common denominator before we can add those fractions together. When we multiply fractions, we can multiply numerators, we can multiply denominators. And when we divide fractions, we know dividing by is the same as multiplying by the reciprocal. And I think some of you refer to that as stay, change, flip. Okay, one thing I wanted to show you on your graphing calculators is how to find absolute value on the TI. So if you want to take a look at your graphing calculator, basically all you're going to do is go into Math, over to Num, and number 1 right there, ABS, is your absolute value. So if you just hit enter, and let's say you want to take the absolute value of a negative number, for example, and notice that the absolute value always results in a positive. So I just wanted to show you real quick on the TI how to find the absolute value key. And the last thing before I show you a couple just real quick examples, scientific form is rewriting a very large number into a number that looks like this. So we have a is equal to c times 10 to the n, and we know the number to the left of the decimal has to be greater than or equal to 1 and less than 10, and n has to be an integer, and that integer could be positive and that integer could be negative. So let me show you just a couple real quick examples before you get started on your homework for section 1.1. The first kind of example that you'll run into in your homework will ask you to rewrite a quantity that contains absolute values without using the absolute values. And they'll give you some kind of restriction on your domain. Remember, your domain are all your values of x that you're inputting into. And so it says if x is less than 1. So you need to pick a value less than 1. So I'm just going to pick if x is less than 1, I'm going to pick x is equal to 0, because we know that 0 is a value less than 1. So I'm going to go ahead and substitute in 0, and when I substitute in 0 into my given absolute value statement, I know that the absolute value of negative 1 is 1. So somehow I need to rewrite this expression without absolute values so that when I substitute in 0 for x, I get an answer of 1 back. Okay, so we need to rewrite x minus 1 without absolute values. So I'm going to go ahead and I'm going to flip this expression. So instead of x minus 1, I'm going to go ahead and just flip it and see if that makes a difference at all. So I'm going to just flip it, again without absolute values, and I'm going to substitute in the same value, which is important. If you choose 0 for with the absolute values, you have to choose 0 for without the absolute values. So look what happens when I substitute in 0 now for x. So I have 1 minus 0, which is 1. So when I come up with that same quantity that I came up with using absolute values, and now without absolute values, we can go ahead and say that the absolute value of x minus 1 is equal to 1 minus x. as long as we have our stipulation on our domain that says if x is less than 1. So this is only true choosing values of x less than 1. The next example wants us to just think of a horizontal number line using the coordinates -5 and -3 on the coordinate line, and it wants us to find the distance between those 2 points. Okay, so really to find the distance, all we're going to do, again, distance is a positive number, so we're going to use the absolute values, and we're just going to go ahead and say -3 minus -5. So that gives me -3 plus 5, which is the absolute value of 2. So it means from -3 to -5 on a horizontal number line, the distance from -5 to -3 on a horizontal number line is in fact 2. We know that if we do a real quick sketch of that. So if this is -5 and this is -3, it basically is saying what is the distance from -5 to -3. So you always just take the 2 coordinates, subtract them, and always include in absolute values because we again are looking for a distance. And one last example, expressing a number in scientific form and also expressing that number in decimal form. So we know, again, to express in scientific form, if my decimal is right here for the number 513, I know that I have to move that decimal as many times as necessary in order to have one number to the left of the decimal that is greater than or equal to 1, less than 10, and then all significant digits afterwards. So if my original number is greater than 1 to begin with, I know my exponent is going to be positive. If my original number to begin with is less than 1, I know that my exponent is going to be negative. So I can rewrite that number 513 as 5.13 times 10 to the positive, because my original number was greater than 1, and I moved it 2 decimal places. So I can rewrite that in scientific form as 5.13 times 10 to the second. And the very last example wants us now to take the number that's in scientific form and put it in decimal form. So again, because my exponent is positive, means I'm going to move that decimal 5 places to the right, and if that exponent is negative, it means I'm going to move it however many units to the left. So I'm going to go ahead and take my number 2.3 and I'm going to move it 5 places to the right. And we know to insert zeros for however many empty spaces we have. And so my new number, therefore, is 230,000.